Alright, I'm Charles, and we're talking about process optimization with Chris. And our goals of process optimization are to set up the optimization problem, and that's the problem that we're going to be trying to make ideal or optimal solutions for. Then we're going to quantify the value of potential improvement. We're going to identify quickly the potential for that improvement. We're going to identify the constraints, the barriers, the bottlenecks, and the things that are basically holding us back from that improvement. We're going to choose appropriate procedures so that we can find the best change that we can do, and then we're going to evaluate the results of this optimization process. Now, but first off, we need to identify what optimization is, and it's defined as the process of improving an existing situation, device, or system, such as a chemical process. And that's what we're really going to be kind of focusing on, is chemical process, being we are chemical engineering students. But first is the decision variables, and there are a couple different kinds of decision variables. First is the decision variable is the independent variable to which the engineer has some control, such as the temperature, discrete variables such as the number of stages in a column. These are things that you, as an engineer, can control and manipulate, just kind of to make the system more ideal or optimize it. Now, the base case for is kind of the starting point for optimization. And in order to identify this, it's necessary to either do a simple flow sheet, maybe a detailed design, and then an actual plan for what you want to improve overall. But the best way to analyze it is what's called a petro-analysis, and that means that you need to focus your attention on what needs to be looked at first. And there's a big kind of rule that people like to implement, which is called the 80-20 rule, which means that 80% of your focus should be on the top 20% of things that are going to be the most either the most profitable or cause the most improvement. So there's no use in spending excessive amount of time on something that's not going to optimize your process, or on something that's not going to give you better results. So you need to spend most of your time on the big game changers. Now here's a little chart on kind of key decision variables, and it's like the arrows disappeared, but the largest improvements are the propylene and the FCI right here. They're a bit taller, but the largest improvements may not necessarily be associated with the largest costs. And to kind of show that right here, when you add the costs into consideration, the utility costs are the largest savings. So that can so by changing the utility costs can change the save the most money throughout the facility. And there are two main optimization types. There's a topological, which is the arrangement of the equipment itself. And then there's also parametric considerations, which are concerned with the operating values, the main ones being the temperature, the pressure, and the concentration of the steams. And to dive in a little bit more about parametric optimization, I'm going to turn it over to Chris.
Okay. So, parametric optimization. The first step is to identify the key decision variables. And those could be like reactor operating conditions, as mentioned earlier, such as temperature, pressure, and concentrations. They could also be separator operating pressures, or single pass conversion values, or reflux ratios, and then trying to recover unused reactants and product purity. Those are all key decision variables that will affect your parametric optimizations. And from those, you can create an objective function. And this is a function that's usually try to set it up in either estimated annual operating cost or net present value, but it's usually a money value. And to start off, you would want to analyze single pieces of equipment, and starting with one variable, then moving on to two variable, and then multivariable. And then you'd move on from there to groups of equipment and analyze those and do the same process. And then you'd want to analyze recycle loops. And recycle loops, when you optimize those, it can affect all the pieces of equipment within it. And you might need to rework the flow sheet and rework economics again. But here's an example of finding optimum reflux in the distillation column. It is a one variable operating function. And some of the things that are fixed in this problem are feed, operating pressure, product yields, and impurities. And from there, the size of the distillation tower is fixed based on the reflux ratio. So the reflux ratio is your one variable. And as R increases, we can see that reboiler duty, size, and utility costs increase, condenser size and utility cost increases, tower diameter increases, and the number of stages and tower height decrease, resulting in our operating function versus the reflux ratio, and you can find an optimum point, an optimal reflux ratio from this. And this is just kind of same idea, but with two variables. In this case, it's temperature and pressure. You can create with your objective function a series of temperature versus pressure curves here. As you can see, each temperature has an optimum pressure, but we're trying to find the optimum temperature and pressure, which would be this bottom extreme there. And moving on from two variables, here's just trying to example of three variable case here. And for three decision variables, we'll have 2 to the third or 8 cases from this. We start with our base case, and we can change each variable from the positive and the negative here, the endpoints, and those are our two decisions there. And anyway, it'll result in 8 different cases that can be analyzed to try to find an optimum net present value or annual operating cost. And that is multivariable. And when considering this, you must also consider flexibility and sensitivity of the optimum. And this could be like the rate at which the operating function changes as a decision variable changes. And it can determine the penalty of failure. Some decisions may have greater effects on net present value. And this is kind of the interplay between optimization and process control to try to find an optimum. And that is it for optimization.